SWT in Eclipse. As an SWT example, now we are focusing on SWT. SWT is an open source widget toolkit for Java designed to provide efficient portable access to the user interface facilities of the operating systems on which it is implemented. The standard widget toolkit provides a common OS independent API for widgets and graphics implemented in a way that allows tight integration with the underlying native Windows system. The entire Eclipse platform UI and the tools that plug into it use SWT for presenting information to the user. Here you can see a demo application on Windows 10. Here you can see communication from Java SWT layer to C native layer, native GTK layer. SWT is a layer between platform UI and the underlying JTK 3 or JTK 4 experimental of the system. It can be launched to use JTK 3 or JTK 4, but cannot use them both at the same time. Communication from Java SWT layer to C native GTK layer occurs through calls defined in os.java. The image here describe this hierarchy better. Here we are considering the Linux environment. Here platform UI is connected to SWT. SWT is connected to os.java. os.java is connected to the SWT underscore JTK3 selection via static calls, and os.java is connected to os.h, and then dynamic calls via flag equal dynamic, and os.h is connected to SWT underscore GTK3 selections. If the SWT underscore GTK3 equals 0, then it's connected to GTK2. If the SWT underscore GTK3 equal 1, it's connected to GTK3. GTK2 and GTK3 are connected to GDK. Now we are considering the widget hierarchy. Widget is the widget is the main widget. Everything else extends widget. The most interesting classes are widget, control, and composite. Most widgets fork off this. As such, it is useful to be aware of fields, methods in parent classes in which methods get overridden by children. In Eclipse, you can control plus click on a method to see its super implementation or derived implementation. This is very useful. The illustration here shows the widget hierarchy. Here widgets interacts with menu, control, scroll bar, item, and tracker. Control interacts with button, label, progress bar, slash, scale, slider, and scrollable. Scrollable interacts with list, composite, and text. Composite interacts with canvas, C combo, cool bar, C tab folder, drill down composite, group, SAS form, scrolled composite, tab folder, table, table tree, toolbar, tree, view form. Here item interacts with cool item, C tab item, menu item, tab item, table column, table item, table tree item, tool item, and tree item. Here we are considering an incomplete diagram of some widgets and their handles in GTK handles. GTK handles are basically GTK pointers to the widgets. When you first look at a widget, you generally first look at the handles that are defined in the widget. For example, each SWT widget is often made up of several GTK widgets or has pointers to GTK widgets. In general, create handle is good place to start when you first look at a widget. Also inspect asterisk handle asterisk methods of the current widget and the widgets above the hierarchy. Parent handle, font handle, child handle, etc. They all contain subsolities which are useful. Handle decorations are inherited, but they are allocated and assigned at a specific widget level. For example, a widget declares handle. Control declares fix handle, but they never allocate them. This will be allocated further down the widget tree. In individual widgets themselves. For example, here is an incomplete diagram of some widgets and their handles. You may observe that the widget has widgets has handle defined. The combo has button handle. Combo has the button handle defined. Here you can see widget and you can see handle here. Control is control inherits widget. You can see fix handle here. Button inherits button and scrollable inherits control. In button you can see box handle, label handle, image handle, arrow handle, and group handle. Text and composite inherits scrollable. In text you can see buffer handle. Combo inherits composite. In combo you can see a button handle, entry handle, text renderer, cell handle, pop-up handle, and menu handle. Here you can see a flowchart describe the process of adding a new function to os.java very well. Here does the function exist in the in os.java already? If it doesn't exist, or no, then it is connected to add method signature to os.java. It is connected to selection do I need to make it dynamic? If it is yes, it's connected to add dynamic flag to method in the os.java, and it is connected to add function signature to os.h, and it is connected to rebuild gtk2 so file. Do I need to make it dynamic? If it is no, then it's connected to rebuild gtk2 os gtk2 so file. It is connected to rebuild gtk3 so file, and it is connected to life is good here, the function. Does the function exist in os.java already? If it is yes, then it's connected to the function. Here life is good. In adding new functions are introduced in JTK3, and old functions are deprecated. In these situations, we need to manually add these method signatures to os.java and os_custom file. Dynamic versus static function. Dynamic functions are not built during compile time. They are only called at runtime. This allows us to have GTK3 functions in GTK4 in a GTK4 build, or run deprecated functions only in GTK3 or some specific GTK strict version range. Dynamic functions have an annotation at method flag equal dynamic. Rebuilding SO files. After you add a new function to os.java and os.h, you need to rebuild the SO file for GTK 3 and GTK4. Dynamics methods and os_custom.h. Before adding a new function to os.java, you should understand dynamic functions. If you inspect os.java and look at the Java doc of some of the functions, you will notice the flag like this at method flags equal dynamic. This means the command is not compiled but called dynamically on the fly runtime. This is useful for functions that are specific for certain versions of GTK. For example, some functions were only introduced in GTK4. As such, this won't compile on the GTK3 build. Such, you made those dynamic. Similarly, some GTK3 functions are deprecated in GTK4, and so that we only use them in GTK3. Thus, we make them dynamic. Not all functions have to be dynamic. You should only make them dynamic if there is a need for it. That is, in general, you should only make functions dynamic if they have to be dynamic. This is because if error does exist, this postpones them from compile time to runtime. Now we are considering debugging SWT, fixed container, and GTK. To debug the C part of a running Java application, you need to attach yourself to the Java virtual machine JVM inside Eclipse. But before doing so, you need to compile GTK and SWT binding with debug flags and optimizations turn off. Here's a diagram to illustrate. Further, since eclipse.platform.swt is a Java project that contains C code, you will have to create a C project that link to that folder to debug the C code. As a note, the source and binaries will be in a different folders, so you will need to create a source and a debug C project. Here you can see Java SWT, and here SWT fixed container and GTK needs to be compiled with debug support and optimizations turn off. SWT fixed contain is connected to GTK here. SWT is connected to GTK here. Here JVM C code we attach to a JVM to debug this part. Here you can see SWT widgets. This is these screenshots for many of the widgets included in SWT. SWT widgets are located in packages org.eclipse.swt.widgets and org.eclipse.swt.custom. Widgets extend either the widgets or the control class. Several of these widgets are depicted in this here. The composite class composite class is a container which is capable of containing other widgets. The group class is another container which is able to contain other widgets. Additionally, draws a border around itself and allows you to set a header for the grouped widgets. Here, browser instance of this class implement the browser user interface metaphor. It allows the user to visualize and navigate through HTML documents. Button class button instance of this class represent a selectable user interface object that issues a notification when pressed and released. Here you can see a SWT button with SWT.arrow and here SWT.push. Here SWT push here. And here SWT.check and here SWT button with SWT.radio. Here button SWT.toggle. Here you can see canvas class canvas. Instance of this class provide a surface for drawing arbitrary graphics. Combo, the class combo. Instance of this class is control. Instance of this class controls that allow user to choose an item from a list of items or optionally enter a new value by typing it into an editable text field. Often combos are used in the same place where the single selection list widget could be used, but space is limited. A combo takes less space than a list widget and shows similar information. Composite, the class composite. Instance of this class are controls which are capable of containing other controls. Coolbar, class coolbar. Instance of this class provide an area for dynamically positioning the items they contain. Class C tab folder. Instance of this class implement the notebook user interface metaphor. It allows the user to select a notebook page from the set of pages. class here date time. Instance of this class are selectable user interface objects that allows the user to enter and modify the date or time values. Expand bar, class expand bar. Instance of this class support the layout of selectable expand bar items. Group, class group. Instance of this class provide an H border with an optional title. Label, class label. Instance of this class represent a non-selectable user interface object that displays a string or image. When separator is specified, displays a single vertical line or horizontal line. Link, class link. Instance of this class represent a selectable user interface object that displays text with links. List, class list. Instance of this class represent a selectable user interface object that displays the list of strings and issues notification when a string is selected. A list may be single or multi-select. Menu, class menu. Instance of this class are user interface object that contain menu items. Progress bar, class progress bar. Instance of this receiver represent represent an unselectable user interface object that is used to display progress, typically in the form of a bar. Shash, class shash. Instance of this receiver represent a selectable user interface object that allows the user to drag a rubber band outline of shash within the parent control. Scrolled composite, class scrolled composite. A scrolled composite provide the scroll bars and will scroll its content when the user uses the scroll bars. Shell, class shell. Instance of this class represent the windows which the desktop or window manager is managing. Instances of that do not have a parent, that is, they are built using the constructor which takes a display as the argument, are described as top level shells. Instances that do not have the parent are described as instances that do have a parent are described as secondary or dialog shells. Slider, class slider. Instance of this class are selectable user interface objects that represent a range of positive numeric values. scale, class scale instance of this receiver represent a selectable user interface object that represent a range of continuous numeric values. Spinner, the class spinner instance of this class are selectable user interface objects that allow the user to enter and modify the numeric values. Styles text, the class style text. A style text is an editable user interface object that displays lines of text. The following style attributes can be defined for the text: foreground color, background color, font style, bold italic, regular, underline, strikeout. In addition to the text style attributes, background color of the line may be specified. Tab folder, class tab folder. Instances of this class implement the notebook user interface metaphor that allows the user to select a notebook page from a set of pages. Table, class table. Instance of this class implement a selectable user interface object that displays a list of images and strings and issues notification when selected. Text instances of this class are selectable user interface objects that allow the user to enter and modify text. Text controls can be either single or multi-line. When a text control is created with a border, the operating system includes a platform-specific inset around the content of the control. When created without a border, an effect is made to remove the insect that such that the preferred size of the control is the same size as the contents. Here you can see text with the SWT.single. Here text with the SWT.multi. Toolbar, the class toolbar. Instance of this class support the layout of selectable toolbar items. Tray, class tray of instance of this class represent the system tray that is a part of a taskbar status area on some operating systems. The instance of this class represent the system tray. Tree, class tree, the instance of this class provide a selectable user interface object that displays a hierarchy of items and issues notifications when an item in the hierarchy is selected. Here you can see a few general terms that are used when discussing layout. When writing applications in SWT, you may need to use layouts to give you a window specific look. A layout controls the position and size of children in a composite. Layout classes are subclasses of abstract class layout. SWT provides several standard layout classes. You can write custom layout classes. In SWT, positioning and sizing does not happen automatically. Applications can decide to size and place composites children initially, or resize or in a resize listener, or they can specify a layout class to position and size the children. If children are not given a size, they will have zero size and they will have cannot be seen. The diagram here illustrates a few general terms that are used when discussing layout. The composite, in this case tab folder, has location, client area, and trim. The size of the composite is the size of the client area plus the size of the trim. The composite has two children that are laid outside by the side. Layout is managing the size and position of the children. The layout is managing the size and position of the children. This layout allows spacing between children and margin between children and the edges of the layout. The size of the layout is the same as the size of the composites client area. The preferred size of the widget is the minimum size needed to show its contents. In the case of composite, the preferred size is the smallest rectangle that contains all of its children. If children have been positioned by the application, the composite computes its own preferred size based on the size and position of the children. If a composite using a layout class to position its children, it asks the layout to compute the size of its client area and then adds the trim to determine its preferred size. Here you can see composite location here XY and composite client area here XY. Here you can see the composite client area with layout width. Here you can see the composite width. Here you can see the trim, and here you can see the trim. Here you can see the height. Here you can see the composite client area height or layout height, and here you can see composite height. As an example, we can consider this code segment. The following is the basic Hello World program using SWT. It shows a window shell and a label. Contrary to swing, display class is necessary to access underlying operating system, and its resources must be explicitly disposed of when they are no longer used. As an example too, we can consider steps to import SWT library. Right click on Java project, click properties. Step 2, click Java build path, then libraries, then add variable, then configure variable. Step 3, click new, then type a new variable name SWT underscore lib in names field. Step 4, click file and browse to SWT library file. PS SWT library is located at Eclipse plugin folder. Its name usually formatted as org.eclipse.swin32.win32.x86 underscore version number.jar. Here you can see the step 2. Click Java build path, then libraries, then add variable, then configure variables. Now we are considering package org.eclipse.swt, SWT constant and error handling support. Now we are considering package org.eclipse.ui.swt, application programming interfaces for interaction with an extension of the Eclipse platform user interface. Now we are considering widgets application structure in widgets. Since the application only displays string hello world, it does not need to register for any widget events. The class label, instances of this class represent a non-selectable user interface object that displays a string or image. When a separator is specified, displays a single vertical or horizontal line. This is in the package org.eclipse.ui.widgets. When you are contributing UI elements using platform workbench extensions, the mechanics of starting up SWT are handled for you by the workbench. If you are writing an SWT application from scratch outside the workbench, you must understand more about SWT's application structure. A typical standalone SWT application has the following structure: create display which represent SWT session, create one or more shells which serve as main windows for the application, create any other widgets that are needed inside the shell, initialize the sizes and other necessary states for the widgets, register listeners for widgets events that needed to be handled, open the shell window, run the event dispatching loop until exit conditions occurs, which is typically when the main shell window is closed by the user. Dispose the display. The following code snippet is adapted from the org.eclipse.swt.examples.helloworld.helloworld2 application. Since the application only displays the string hello world, it does not need to register for any widgets events. The display represents the connection between SWT and the underlying platform's GUI system. Displays are primarily used to manage platform event loop and control communication between the UI thread and other threads. For most applications, you can follow the pattern that is used here. you must create a display before creating any windows, and you must dispose of the display when your shell is closed. You don't need to think about the display much more unless you are designing a multi-threaded application. Shell. A shell is a window managed by OS Platform Window Manager. Top-level shells are those that are created as child of the display. These windows are the windows that users move, resize, minimize and maximize while using applications. Secondary shells are those that are created as a child of another cell. These windows are typically used as dialog windows and other transient windows that only exist in the context of another window. Parents and children, in all widgets that are not top-level shells must have a parent. Top-level shells do not have a parent, but they created associated with a particular display. You can access the display using getDisplay. All other widgets are created as descendants, direct or indirect, of top-level shells. Composite widgets are widgets that can have children. When you see application window, you can think of as a widget tree and hierarchy that roots is the shell. Depending on the complexity of the application, there may be a single child of shell or several children or nested layers of composite with children. Style bits. Some widgets properties must be set at the time a widget is created and cannot be subsequently changed. For example, a list may be a single or multi-selection and may or may not have scroll bars. These properties called styles and are set of the constructor. All widgets constructors take an int argument that is specified bitwise or of all desired styles. In some cases, a particular style is considered a hint, which means that it may not be available on all platforms but will be gracefully ignored on platforms that do not support it. The style constants are located in the SWT class as public static fields. A list of applicable constants for each widget class is contained in the API reference for SWT. Resource disposal. Platform underneath SWT require explicit allocation of freeing of OS resources. In keeping with SWT design philosophy of reflecting the platform application structure in Widget Toolkit, SWT requires that you explicitly free any OS resources that you have allocated. In SWT, the widget dispose method is used to free resources allocated with the particular toolkit object. The rule of thumb is that if you create the object, you must dispose it. Here are some specific ground rules for further explain the philosophy. If you create a graphic object or widget using a constructor, you must explicitly dispose of it when you are finishing and using it. When a composite is disposed, the composite and all of its child widgets are recursively disposed. In this case, you don't need the disposed of widgets themselves. However, you must free any graphic resource allocated in conjunction with the widgets. If you get any graphic object or widget without using a constructor, for example control.getBackground, do not dispose of it since you did not allocate it. If you pass a reference to your widget or graphics object to another object, you must take care not to dispose all of it while it is still being used. If you create a graphic object for use during the lifetime of one of your widgets, you must dispose of the graphics object when the widget is disposed. This can be done by registering a dispose listener for your widget and freeing the graphics object when the dispose event is received. There's one exception to these rules. Simple data objects such as rectangle and point do not use operating system's resources. They do not have dispose method, and you do not need to have to free them. If in doubt, check the Java doc for the particular class. Now we are considering events. This simple example is adapted from the org.eclipse.swt.example.helloworld.helloworld3. The class control adapter. This adapter class provides the default implementation for the methods described by the control listener interface. This is in the package org.eclipse.swt.events. Once we create a display and some widgets and start up the application's message loop, where does the real work happens? It happens every time an event is read from the queue and dispatched to the widget. Most of the application logic is implemented as a response to the user event. Basic pattern is that you add the listener to some widget that you have created, and when the appropriate event occurs, the listener will be executed. This simple example is adapted from org.eclipse.swt.examples.helloworld.helloworld3. For each type of listener, there is an interface that defines the listener XYS listener, a class that provides the event information, XYZ event, and an API method to add the listener, add XYZ listener. If there is more than one method defined in the listener interface, then there is an adapter, XYZ adapter, that implements the listener interface and provides the empty methods. All of the events, listeners, and adapters are defined in the package org.eclipse.swt.events. Now we are considering layouts. The next snippet uses a layout to achieve the same effect. Class fill layout. Fill layout is the simplest layout class. It lays out controls in a single row or column, forcing them to be the same size. This is in the package org.eclipse.swt.layout. Often the best way to handle simple widget positioning is in the resize event listener. However, there are common patterns used by applications when placing widgets. These patterns can be structured as configurable layout algorithms that can be reused by many different applications. SWT defines layouts that provide general purpose positioning and sizing of a child widgets in composite. Layouts are subclasses of the abstract class layout. The SWT standard widgets can be found in the org.eclipse. Layout. There are some general definitions used when resizing and positioning widgets. The location of a widget is its XY coordinates location within its parent widgets. Preferred size of a widget is the minimum size that needed to show its contents. This is computed differently for each kind of widgets. The client area is the area which the child can be placed without being clipped. Trim is the distance between the widget's client area and its actual border. Trim is occupied by the widget's borders or extra space at its edge. The size of appearance of a trim is widget and platform dependent. These concepts are relevant for application regardless of whether a layout is used. You can think of a layout as a convenient way to package resize functionality for reuse. Some additional concepts are introduced by layouts. Some layouts support spacing between widgets in the layout. Some layout supports margin between edge of the layout and widget displacement widget adjacent to the edge. The following code snippet shows the simple case of an application using resize callback to the size of a label to size of its parent shell. Next snippet here uses the layout to achieve the same effect. Even for this simple example, using a layout reduces the application code. For more complex layout, the simplification is much greater. Here the fill layout. Fill layout is simplest layout class. It lays out control in a single row or column, forcing them to be the same size. This is in the package org.eclipse.swt.layout. Now we are considering SWT UI thread in threading issues. The main thread, including the event loop for an SWT application, has the following structure. The class display, the instances of this class are responsible for managing the connection between SWT and the underlying operating system. Their most important function is to implement the SWT event loop terms of the platform event model. They also provide various methods to accessing information about the operating system and have overall control over the operating system resources which SWT allocates. This is in the package org.eclipse.swt.widgets. The SWT follows the threading model supported directly by the platform. The application program runs the event loop in its main thread and dispatches the event directly to this thread. UI thread is the thread in which the display was created. All other widgets must be created in the UI thread. Since all event code is triggered from the application's UI thread, application code that handles events can freely access the widgets and make the graphics calls without any special techniques. However, the application is responsible for forking the computational threads when performing long operations in response to an event. Note, the SWT will trigger SWT exception for any calls made from non-UI thread that must made from the UI thread. The main thread, including the event loop for SWT application, has the following structure. Once the widgets are created, the shell is opened and the application reads and dispatches the event from the OS queue. Until shell window is disposed. If there are no events available for us in the queue, we tell the display to sleep. to give other application a chance to run. SWT provides special access method for calling widgets and graphics code from the background thread. Start the event loop. We stop when the user has done something to dispose our window. Now we are considering SWT exception in error handling. SWT exception is thrown when a recoverable error occurs internally in SWT. The error code and the message text provide the further description of the problem. The class SWT exception. This runtime exception is thrown whenever a recoverable error occurs internally in SWT. The message text and error code provide the further description of the problem. The exception has a throwable field which holds the underlying exception that caused the problem. If this information is available, that is, it may be null. This is in the package org.eclipse.swt. SWT exception is thrown when a recoverable error occurs internally in SWT. The error code and message text provide the further description of the problem. SWT remains a stable state after throwing the exception. For example, this exception is thrown when the SWT call is made from a non-UI thread. Now we are considering painting in graphics object life cycle. In graphics, the color red was previously allocated when creating the widget, so it can be used here. The class GC is where all drawing capabilities that are supported by the SWT are located. Instances are used to draw on either an image, a control, or directly on a display. This is in the package org.eclipse.swt.graphics. Once you have allocated your graphics object, you are ready to paint. You should always do your painting inside the paint listener. There are rare cases, particularly when implementing custom widgets, when you paint while responding to some other events. However, this is generally discouraged. If you think you need to paint while handling some other event, you should first try to use redraw method, which will generate another paint event in the OS. Drawing outside of the paint method defeats the platform optimizations and cause bugs depending upon the number of pending paints in the event queue. When you receive a paint event, you will be supplied with the GC pre-configured for drawing the widgets. Do not free this GC. You did not create it. Any other graphics object must be allocated while handling the event or beforehand. Below is a snippet on the org.eclipse. SWT.examples.helloworld5 example. The color red was previously allocated when creating the widget, so it can be used here. Here you can see hello world in SWT examples. Now we are considering SWT application wizard. Um, this wizard generates the following code including main. SWT application window SWT application window wizard creates a main class that instantiates and shows the top level shell. The wizard can be selected from the drop down menu or from the Eclipse new wizard. To use the wizard, select the project source folder and the package that contain the class, and enter the class name to and hit the finish button. The wizard generates the following code including main method. When editing SWT applications in Windows, all of the SWT layouts, all of the standard SWT layouts containers and widgets and menus are available. Custom or third-party control may be added via the choose component command. Now we are considering SWT composite wizard. The wizard generates the following code. Subclass of the SWT composite class can be created using SWT composite wizard. The wizard can be selected from the drop down wizard menu or from the Eclipse new wizard. To use the wizard, select the project source folder and package that contain the class and enter the class name. Then hit the finish button. The org.eclipse.widget swt.widgets.composite class is the default superclass. You can select org.eclipse.swt.widgets.group as the superclass if you prefer. The wizard generates the following code. When editing SWT composites, all the standard SWT layouts, containers, widgets, and menus are available. Custom or third-party controls may be added via the choose component command. Disable the check that prevents subclassing of SWT components. Now we are considering SWT dialog wizard. The wizard generates the following code, including open method. Subclass of the SWT dialog class can be created using SWT dialog wizard. The wizard can be selected from the drop-down wizard menu or from the Eclipse new wizard. To use the wizard, select the project source folder and the package that contain the class. Enter the class name and hit the finish button. The org.eclipse.swt.widgets.dialog class is the default superclass. The wizard generates the following code, including the open method. When editing dialogues, all the standard SWT layouts containers and widgets and menus are available. Custom or third-party controls may be added via the choose component command. SWT shell wizard. The wizard generates the following code, including the main method. Subclass of the SWT shell class can be created using the SWT shell wizard. The wizard can be selected from the drop-down wizard menu or from the Eclipse new wizard. To use the wizard, select the project source folder and the package containing the class. Enter the class name and hit the finish button. org.eclipse.swt.widgets.shell class is the default superclass. The wizard generates the following code, including the main method. When editing SWT shells, all of the standard SWT layouts, containers, widgets, and menus are available. Custom or third-party controls may be added via the choose component command. Disable the check that prevents subclassing of SWT components. Now we are considering object SWT fields in RIP web client API reference. Here is static SWT.alt, keyboard or mouse event mask indicating that the alt keys was pushed on the keyboard when the event is generated. This is in the object SWT. This object defines the public constants used by RWT scripting, specifically event types and key codes. Now we are considering event code generation in event handlers, in code generation, in preferences in SWT. This preference determines how event handlers are generated. First option, create anonymous class, generates anonymous adapter class located in line with the widget definition. Second option is create inner class, generates an adapter class as an inner class. Options are provided to add inner class at the beginning or end of the class, as well as specify the pattern used to name the inner class. The pattern can include the template variables names enclosed between $ open curly brace and close curly brace shown here. Capitalizing the name of any variable will cause the value of the variable to be capitalized before it is inserted into the resulting text. The pattern can include component name, the name of the component to which the handler is being attached, component class name, the name of the class of the component to which handler is being attached, listener name, it's not there, the name of the event being handled, listener class name, name of the event listener, third option is implement the listener interface in parent class, adds the listener interface to the parent class and adds the appropriate method to the class definition. Here you can see the example. Here you can see Forms API. This page is used to control SWT Forms API options. Generate paint border for method for new composites. This preference control whether a call to paint border for method is generated for each added composite. When borders are turned on for a composite, various widgets are automatically drawn with the flat border. When borders are turned off, widgets are drawn without borders. Automatically adapt method new non-form controls. This preference whether new form controls are automatically adapted using the form toolkit. Now we are considering absolute in layouts in SWT in preferences. This page is used to control various SWT, then layouts, then absolute options. Here use free component placement style. This preference determines whether free mode is used for aligning widgets. Free modes uses widget snapping similar to that used for group layouts. Component gaps. This preference determines the default gaps are used between components and their containers in free mode. Container gaps. This preference determines what default gaps are used between components and their containers in free mode. Apply grid creation flow. This preference determines whether the creation order of the widgets will be adjusted to reflect their position in left to right or top to bottom grid flow. This will affect the default tab border. Use grid snapping. This preference determines whether grid mode is used for aligning widgets. Grid mode uses use a customized snapping grid. Grid step. This preference determines the grid step used in the grid mode. Display grid. This preference determines whether the grid is displayed in grid mode. Display locations and size hints. This preference determines whether location and size hints are shown when moving or sizing widgets. Automatically resize component on text or image property change. This preference determines whether a widget is automatically auto-sized anytime its text or image property is changed. Now we are considering preference page. This page is used to control various SWT preference page options. Editor use same code generation settings as control. This preference determines whether new field editors use the same code generation settings as new controls. Now we are considering new SWT bindings in SWT data bindings. When creating a binding, the update strategy from target to model and model to target may be specified. As well as any strategy specific properties validators and converters. New bindings are created by selecting target, a target property, a source or source property, and clicking the bind button. When creating binding, the update strategy from target to model and model to target may be specified, as well as any strategy specific properties, validators and converters. When the target or model is a text widget and text property is selected, the triggering event may be specified as SWT dot modify, SWT dot focus out, or SWT dot none. Predefined update strategies, predefined update value strategies, policy underscore update, policy underscore never, policy on request, and policy convert may be selected, or custom or a custom strategy class may be chosen. Now we are considering main features of absolute layout. Select absolute layout from the layout panel. Layout palette, and drop it on the window or composite. Absolute layout or null layout is a simple XY oriented layout. During layout, the live component is shown moving with the tooltip showing its current location or size. Dynamic snap or alignment points are provided to make the convenient to align the composite with other component, or the window margin. Resizing a component also snaps to the preferred size of the resized component, or to the size vertical or horizontal of any other component on the same parent. Graphical feedback is provided for all widgets size and position operations. Now we are considering main features in SWT fill layouts. Select fill layout from the layouts palette, and drop it on the window or composite. Fill layout is the simplest layout class. It lays out controls in a single row or column, forcing them to be the same size. Initially, the controls will be as tall as the tallest control, and as wide as the widest. Fill layout does not wrap, but you can specify margins and spacing. You might use the two layout buttons in this taskbar, or in a taskbar or toolbar, or to stack checkboxes in a group. Fill layout can also be used when a composite only has one child. For example, if a shell has a group child, fill layout will cause the group to completely fill the shell if margins are 0. Graphical feedback is provided for all drops and move interactions. The spacing can be specified using property pane. Now we are considering main features in form layout. Select form layout from the layouts palette and drop it on window or composite. A form layout class that implements an constraint based layout manager. With constraint based layout, you have independent control over sizing and over the sizing behavior of each of the 4 sides of the widget. The top, bottom, left and right sides can be independently attached to the sides of the parent container or sides of any sibling widget within the same container using either fixed or relative offsets. This proves to be surprisingly powerful and can be used to emulate almost any of the other layout managers. The form layout class is very simple and only specifies the margins of the container. The real power is in the form data object, which hold up our 4 element form constraint objects. The graphical feedback is provided for all widget size and position operations. Support for automatic placement mode and classic mode. Now we are considering main features in grid layout. Select grid layout from the layout palette and drop it into a window or composite. Grid layouts lays out the control children of a composite in a grid. The grid layout has a number of configuration fields. And the controls it lays out can have the associated layout data object called grid data. The power of grid layout lies in ability to configure grid data for each control in the layout. Num columns field is the most important field in the grid layout. Widgets are laid out in columns from left to right, and a new row is created when the number of columns num columns plus 1 controls added to the composite. Graphical feedback is provided for all column, row, and cell interactions. Column and row properties may be changed via a pop-up menu, and convert existing layout from layouts null from form layout etc. to grid layout with intelligent column and row creation. Now we are considering main features in SWT group layout. Select group layout from the layouts palette and drop it on a shell or composite. Group layout is a layout manager hierarchically groups components in order to the position them in a container. Group layout is intended to use by builders but may be hand coded as well. Grouping is done by instances of the group class. Group layout is intended for use by builders but may be hand coded as well. Grouping is done by the instances of the group class. Group layout supports 2 types of groups: sequential groups and sequential group positions its child elements sequentially and one after another. The parallel groups aligns its child element in one of 4 ways. Each group may contains a number of elements where an element is a group component or gap. A gap can be thought of as an invisible component with a minimum minimum and preferred and maximum size. In addition to group layout supports the preferred gap whose values come from layout style. elements are similar to a spring. Each element has a range and as specified by the minimum, maximum, and preferred size. Gaps have either developer specific range or a range determined by layout style. The range for components is determined from the components get minimize size, get preferred size, and get maximum size methods. In addition, when adding components, you may specify a particular range to use instead of that from the component. The range for a group is determined by the type of group. The parallel group's range is maximum of the ranges of its element. The sequential group's range is sum of the ranges from its elements. Group layout treats text each axis independently. That is, there is a group representing a horizontal axis, and the group representing vertical axis. The horizontal group is responsible for determining the minimum preferred and maximum size along the horizontal axis, as well as the setting the x and width of the component contained in it. Vertical group is responsible for determining the minimum preferred and components contained in it. Each component must exist in both a horizontal and vertical group, otherwise an illegal state exception is thrown during layout or when the minimum preferred or maximum size is requested. Graphical feedbacks is provided for all widget size and position operations. Now we are considering main features in SWT row layout. Select row layout from the layout palette and drop it on a window or composite. Row layout determines the size and position of children of a composite by placing them either horizontal rows or vertical columns with the parent's composite. Row layout aligns its control in one row if the type is set to horizontal, and one column if the type is set to vertical. It has the ability to wrap and provide configurable margins and spacings. Row layout has a number of configurable fields. In addition, height and width of each control the row layout can be specified by setting the row data object into the control using set layout data. The graphical feedback is provided for all drop and move interactions. Spacing can be specified by property pane. Now we are considering main features in stack row layout. The select row layout now we are considering main features in SWT stack layout. Select stack layout from the layouts palette and drop it on the window or composites. Stack layout object is a layout manager for container. It treats each component in the container as a card. Only one card is visible at a time, and the container acts as a stack of cards. First component is added to the stack layout object is the visible component when the container is first displayed. The ordering of card is determined by the container's own internal ordering of its components objects. Stack layout defines a set of methods that allow an application to flip through these cards sequentially or to show the specific card. When adding a new widget, the current drop point is highlighted in green. switch between cards, use the using the up down arrows in the upper right corner. Now we are considering main features in swing border layout. Select border layout from the layout palettes and drop it on a window or composite. Border layout lays out the container, arranging and resizing its component to fit 5 regions: north, south, east, west, and center. Each region may contain no more than one component and is defined by the corresponding constant north, south, east, west, and center. When adding component to the container with the border layout, use one of these 5 constants as convenient. And as convenient, border layout interprets the absence of a string specification, same as the constant center. Graphical feedback is provided for all drop and move interactions. Horizontal and vertical gaps can be specified by using the property pane. Now we are considering main features in swing box layout. Select box layout from the layouts palette and drop it on the window composite. Box layout box allows multiple components to be laid out either vertically or horizontally. Components will not wrap. So, for example, vertical alignment of component will stay vertically arranged when the frame is resized. Nesting multiple panels with different combinations of horizontal and vertical gives an effect similar to grid back layout without complexity. Box layout manage is constructed with an axis parameter that specifies the type of the layout that will be done. For all directions, components are arranged in the same order as they were added to the container. Box layouts attempts to arrange the components at their preference widths for horizontal layout or heights for vertical layout. For horizontal layout, if not all the components are in the same height, box layout attempt to make the components as the highest component. If that is not possible, for a particular component, the box layout aligns the component vertically according to the component's Y alignment. Of 0.5, which means that the vertical center of the component should have the same Y coordinate as the vertical centers of the other component with 0.5 alignment. Similar for a vertical layout. Box layout attempts to make all components in the column as wide as the widest component. If that fails, aligns them horizontally according to their X alignments. Graphical feedbacks is provided for all drop and move interactions. Graphically show area occupied by struts and springs. Now we are considering compatibility to SWT in differences between RWT and SWT in RAP widgets toolkit. Here you can see the example. RAP generally follows the rule: if it compiles, it works. That means that all SWT API implemented in RWT is working within the requirements set by SWT. If an SWT feature is not implemented, the corresponding API is also missing. If this is the case, it is likely because it's hard or impossible to implement in RWT. In some cases, SWT classes and methods are implemented as empty stubs to enable a single single sourcing, but only where this is valid according to SWT documentation of AP. Examples are accessing API and some SWT constants that are marked as hint. SWT has developed for desktop application, but RWT is used to build a web application. For this reason, there are some features that SWT supports that RWT does not, while RWT adds some features that are tailored to the specific requirement of web application development. However, RWT does not add any new API to the classes adapted from SWT. All RWT specific features are accessible by API in the namespace org.eclipse.rap.rwt. Many are activated using widgets setData method with the constant from RWT class as the key example here. Other additional features may be accessed via client services. Now we are considering local variable mode in variable generation in SWT, code generation in bidirectional code generation in features in window builder. In local variable generation style, each component is assigned to the unique local variable and initialized at the point of declaration. An option is provided to declare each variable as final. Note that component types marked as final on the variable, then type specific reference page will always be assigned to fields. As an error example, we can consider this. An SWT error has occurred. You are recommended to exit the workbench. Subsequent error may happen and may terminate the workbench without warning. See the .log file for more details. Exception struct trace org.eclipse.swt.swt error. No more handles at org.eclipse.swt.swt.error swt.java 4517 at etc. Now this is the end of my presentation. Thank you very much for watching it.